Perceptron. Before we see what is perceptron, why ANN is used, that is artificial neural network is used. So as I told in the previous slide, or we have input layer, we have hidden layer, then we have output layer. They are connected to one another, forming the network. So this is what is called as artificial neural network. Fine. Now, what is the job of artificial neural network? Fine. Or why this artificial neural network they are used? This artificial neural network they are used to learn, or ANN learn by adjusting the weights of the connections between the neurons based on the differences between their predictions and actual values in the training data set. So whenever we have an artificial neural network, we'll be having the predicted values as well as the actual values. Actual values are the one that is present in the data set. So based on these two values, what we are going to do is we are going to learn the weights, or we are going to adjust the weights. Fine. Why? Because so that we get the same actual output or actual values as present in the data set with all the combinations of inputs that are given at the input layer. Right. Now, with this, when it comes to the perceptron, since we have a neural network which consists of more than one neurons, where one neuron is connected to the other neuron. Now, instead of completely analyzing the processing of the complete network, what we'll do is we'll see how actually a single node performs the processing operation by taking the input. That is what a single neuron. So a single neuron is called as what? It is called as a perceptron. Right. Now, when it comes to perceptrons, so as I told, what are perceptrons? So a perceptron is a single neuron, or a single neuron is called as a perceptron. It is not a McCulloch and Pitts model. It is the modified version of the McCulloch and Pitts model. It can also be considered as a type of artificial neural network system. It takes a real vector. It takes a vector real value input, calculate the linear combination of these inputs and outputs, the results. Okay, that is +1 -1 if it is a signum function, or it is +1 and 0, it is a step function, and also based on the threshold value. If it is greater than the threshold, then it returns +1. If it is less than the threshold, it returns -1. Right. Now with this, we'll see how actually a single neuron performs the operation, or how it's going to process the input. So as we know, we have the input to a neuron. It is not a single input. We can have a number of inputs. I'll take these inputs as x1, x2, x3, and followed by xn. So as we already saw, a simple or a McCulloch Pitts model. So each of the input, they are associated with the individual weight. So if I just give, so we have the individual weights. So I'll represent these weights as W1, W2, then W3, and this is followed by Wn. Now, since it is a modified model of the McCulloch and Pitts model, so we have one more input, a constant value, that is called as bias. Usually, you can also consider that as W0, where the value for this is always represented with 1. So this bias, why we are using, it is a constant value that is going to help the activation function, fine, in giving the output. So whenever we have inputs, outputs, so it is always going to give what? The weighted sum. So this is what the summation it will do. So what is the output from this input and the weights now? So I'll represent that with Z, where this is the value, that is summation of I equals to 1 to n, that is Wi into xi plus we are going to take the bias value. Why not this one? This one, because there is always a constant and this value is always a 1. But whereas the x value, it can be some other value, 0 or any other value. So since this bias is always a constant value, I want to retain the value as it is. That is going to help the activation function to map the input signals to the output signals, and keeping this as what? Plus b. So this is the output, or this is the weighted sum. So this is what we have, the weighted sum. Yes, now this input is given to the activation function, because this is the one that is going to map the output. So we are going to give it to the activation function. Fine. So here, for example, I'll consider here the activation function is the signum function, where we have +1, -1 based on the threshold value. So from here, we are going to get the output. Fine. So here output is represented as 0. The output of the activation function is 0. Finally, we are going to have the output. Whatever we are going to get from the activation function, that is the output. Now, what is this output? How this will be calculated? This output, oh, it is nothing but, I'll represent this activation function as sigma. So sigma of, what is the input to this activation function? That is this summation, correct? So this is sigma of I equals to 1 to n, that is wi into xi plus b is what? The input to the activation function. So what is the output that I'm going to get from the activation function? It is +1. Fine. If what? This is greater than or equal to 1, that is if wi xi plus b value is greater than or equal to 1, or greater than or equal to, sorry, 0, then -1 if xi plus b otherwise. So since I'm using sigma function is this. If I be use step function, then it is +1 and it is 0. Right? So this is the working of one single neuron. Right? So this is the working of one single neuron. Like this, in artificial neural network, we can have more than one neurons. So this is a simple perceptron, a single neuron, and this gives the working of your single neuron. Fine. So with this, we'll see what is the representational powers of the perceptron. The perceptron are usually represented as a hyperplane, that is in n-dimensional space, something like this. Fine. And this perceptron, they represent very well all the Boolean functions like hand or land and nor, etc. Because all these things are binary values. So this works well whenever we have a binary class or a two class problems, something like, okay, either classify to this category or classify to this particular class. And unfortunately, even though it represents almost all the primitive Boolean functions, some Boolean functions cannot be represented by using what? By using a perceptron. Example is XOR, because this XOR, when represented in the hyperplane, it becomes always the non-linear function, whereas these are the linear one. So hence these cannot be represented by a perceptron. Fine. Now, we'll see, okay, how can do perceptron classify, correct? Now, if that is the case, if I have something like this, okay, I have dimension x as well as y, fine. Now, I have value something like two binary values. One is something like plus, okay, I'll consider this as +1, and other class with different class label, something like this one, -1. Fine. Now, what is the function that is going to divide this class and this class is what we need to identify. So what is this linear function? So I need to identify what is this linear function that is going to divide this set of class from this set of class. So this is how the perceptron classifies. That is what we are doing. How can do a perceptron classify? We are not learning here how to adjust the weights, that will take in the next slide. Here we'll see how do actually a perceptron classify. Now suppose if I consider there are two input, that is what I have given. This is x and y. X and y are my input. Fine. So what we'll do here, each of the input they are associated with the weights. I'll represent it with wx and wy. I have the bias value. I'll do the summation here. This is given to which one now? The activation function. I'll write this as my activation function. Finally, what we are going to get the output. Now, for example, if I take the bias value as 0, fine, and wx weight is fixed something like minus 0.5, fine, then wy is the weight of the y input, that is 0.5. This is minus 0.5, this is 5. Then what is the linear function? What is this equation that is going to classify this with this? So what we'll do is, what this is going to do, this is going to do the summation. So it is nothing but what? X into wx plus y into wy plus the bias value, which is equal to 0. So x value, because since I'm finding the general linear function, so whatever the next input that is given, if I give that input to this function, then it has to correctly classify whether it belongs to this class, that is plus 1, or whether it belongs to minus 1. So value is what? This is wx value is minus 0.5 plus y, this is 0.5, which is equal to 0. So what I'll get now, it is y 0.5 into y equals to then 0.5 into x. So this is finally y is equal to x. So this is my function. So this is my function that is going to classify these values from these values. So this is how we are going to classify with the help of the perceptron. Fine. Next, we'll see how to learn the weights of a single perceptron. So, the weights of the single perceptron, it is a precise learning problem, and it is used to determine the it is used to determine what? The weight vector. So, weight vector. So, this is what we are into. So, we are learning. It is what we are going to learn or adjust the weight vector that causes the perceptron to produce the correct output, that is plus or minus 1 for each of the given training example. So what we have to do, we have to keep in this in mind in learning the weights of the perceptron by keeping in mind what is the given training examples. Right. So we have two important rules from where we can learn the weights of the perceptron. So we have two rules. Fine. The first one, it is called as perceptron rule. Fine. The second one, it is called as delta rule. Now, first, initially, we'll see how to use the perceptron and to learn the weights. And later, we'll see with the delta rule. So, this is important because they provide the basis for learning the networks of many units. So, that's why we need to learn the weights. Now, we'll see, today we'll take the first, so this is what, this is their important. Now, with this, we'll take the perceptron training rule. So when it comes to the perceptron training rule, so we need to modify the weights. So the weights are modified at each step according to the perceptron training rule, which senses the weights wi associated with the input xi. According to the rule, what we are going to do is, okay, so we are going to change the value of the weight by taking the current weight associated with the input plus delta wi. So what is this delta wi? So delta wi is equal to some value nu into t minus o into xi. Fine. So here, or finally, you can also write something like wi, or change the value of the weight plus, you can directly write t minus o into xi. So this is the input value. Okay, this is the weight associated with this input. This is the new weight. This is the weight, previous weight. So we are going to learn the weights. The new weight is this one for this particular input. So where T is what? The T is the target output. So this target output is available from the training example. O is what? O is the generated output from the perceptron. What is this O generated from the output of the perceptron? So you know you have x1, x2, w1, w2 associated. We have the summation. This is given as an input to which one now? The activation function. From the activation function, you are going to get this output. So this is what this O is representing. Output generated by the perceptron. It is nothing but this is the obtained output from the perceptron. This is the target output that is available in what? That is available in the training example. If I just do T minus O, that is the actual output minus the obtained output. Obtained output is this from the perceptron. Target output, it is always available in the training example. When you take here T minus O, this is what is considered as an error. So we should see that this error does not come. Why this error comes? Because of these weights. So whenever we get the error, we need to adjust these weights so that these weights, whatever the weights we are going to consider, it works fine. The same weights work fine for all the set of inputs. First time maybe the input with x1 and x2 has something like 0.1 and 0.2. So for the same weights, it has to work fine such that whatever the obtained output we have, it must be same as what? The target output. Fine. Next time when I give the new set of inputs for x1 and x2 for the same weights, even it has to give the output where this obtained output must be same as that of the training example. To have that, what we are supposed to do is we need to learn these weights. So how we are going to modify the weights whenever we get the error, that is difference between this particular term, then we'll be using this formula. So this formula, it is called as perceptron training rule. Fine. Now with this, we have an algorithm, fine, which is called as the perceptron algorithm. Fine. So what we do is the perceptron training algorithm, or the it consists of two inputs. One is X, okay. Then again the next one is new. So this is called as learning rate. So what is learning rate here? Learning rate is a positive constant. Fine. It is a positive constant, so it is not going to change. So which is going to moderate the degree to which the weights are changed at the each step. So we need something that is going to balance the weights, because each time the weights keep changing whenever we have an error with this. It is nothing but T minus O, we are having error. If we get 0, then no error. If we get some other value, then there is an error. So what we'll do is if we get 0, then it is no error. So whenever we get an error, we need to update the weights. For doing so, we need something that is going to balance it. And for that, we are going to take a rate that is called as learning rate. So that is an input to your perceptron training rule. Then initialize W. W, initially, whenever we have a perceptron, the weight values will not be given. So we can assume some random values as the initial weights for the inputs. Because we are assuming some weights, initial weights as an input, we need to learn the weights and fix that particular weights so that it works with all the sets of inputs and giving what? The correct output. Okay, that is equivalent to that of what? The target output present in the training set. So repeat this for each training instance, that is x comma tx. Tx is nothing but the training examples, that is the labels, belongs to x. X is nothing but the data set. Compute the real output. Output is nothing but this is what the output from the perceptron. I told it is nothing but for the activation function we are going to give the weighted sum. So this is going to return some value based on what activation function we are using, whether it is a signum function or a step function. Fine. If the target output is not equal to the obtained output, so this is your obtained output, then what we'll do, we'll update the weights. If they are not equal, we'll update the weights. If they are equal, that is nothing but if we get the value 0, T minus 0 as 0, that is target output minus the obtained output as 0, then no need to update the weight. Otherwise, we need to update the weight by using this formula. This is called as perceptron training rule. This is called perceptron training rule. we are going to use this and update the weights, and finally end for until when, until all the training instances in X are correctly classified. It is nothing but whatever the instance, whatever the set of inputs you give, it has to correctly classify according to the training example that are given. Until then, we should go on updating what? We are go on updating the weights. And this is what is called as the perceptron algorithm or perceptron training rule. If they ask you people with the perceptron algorithm, you're supposed to write this. Okay, we'll see, we'll take up the next problem and we'll see how actually the perceptron algorithm can be used in doing the classification.